Hello everyone. In this video, we're going to take a look at a CVE in the Windows kernel, the bug that caused it, and how to go about writing a script in Binary Ninja to find it automatically. This bug was brought to my attention by one of the students in a recent training class we had. At the end of the week, we like to leave time for topics chosen by the students, and this class wanted to delve into a real-world example. Turns out, the simple case is super easy to model, and we had a working script automatically detecting bugs in just a couple of minutes. Now, I'm not going to cover all the background information you might want to know to model this bug. We spend almost a week talking about that in our training class, but I do want to talk about how you'd approach this problem and how to get something working in a pinch. Secureless.com put a nice blog post out detailing the bugs. I'll include a link to it in the description. And if you scroll down a bit here, you can see the bug right here. The problem is that there's a subtraction inside of a comparison, but the right-hand side of the subtraction is not properly bounded. This meant that the right-hand side of the subtraction could become greater than the left-hand side, which in an unsigned comparison could lead to an integer underflow and bypass of this check. So I have this open in Binary Ninja, and I have two copies. I've got one that has the vulnerable subtraction in it, and I have a version where that was fixed. I've gone ahead and marked these up a little bit to make them easier to read, but you can see exactly what they were talking about in the blog post, where we've got this vulnerable subtraction inside of an unsigned comparison, and this new version is different. So how do we automatically detect this vulnerability? We'll need to model it in code, and we're going to use Binary Ninja's API to script across every instruction and try to identify this pattern. But then how do you model this pattern? Well, when it comes to modeling vulnerabilities, there's a trade-off between how specific you want to be, how many false positives you're okay with, and how much time you want to spend engineering it. Today we're going to be super specific so we can find just this bug, and maybe some like it, but we're not going to spend much time writing the code. This will open us up to false positives, but I'll touch on that a little bit at the end of the video. So first things first, we're going to use one of our official plugins to write our script. This will give us just a slightly more seamless experience, but I don't recommend it for things larger than just a handful of lines. Start by opening up the plugin manager by pressing Ctrl-Shift-M or Command-Shift-M. Then search for snippets. You can see that it's an official plugin because it's in orange and made by Vector35. And in the bottom right, you can go ahead and click install. Now in the menu bar at the top here, we should have plugins, snippets, snippet editor. We'll go ahead and make a new snippet, and I'm going to call it CVE 2021 31955. And we'll start by first cycling through all the decompilation instructions in this binary. And we'll go ahead and print those out. I'll click run just to make sure that's working. A little bit of typo there. And there we go. All the decompilation is being printed out to the console. Great. And now it's time for the hard part, matching against this pattern. I like to use Python's match syntax for this. Sometimes it's overkill, but I like to use it to destructure the IL, and in more complicated cases, it becomes even more useful. It can be a bit tricky knowing exactly what you want to destructure here, so if you're ever stuck, you can go down to the Python console and use some of the magic variables we provide. We support tab completion, so current_tab will show you most of the magic variables that are available. We'll just go ahead and use the current IL instruction. And what we want from that is we want to type high-level ILF. We can copy and paste this into our script, and let's just go ahead and see what that does. Again, we have to go over to our log, and we'll see that it's printing a lot of if statements. Since we're being hyper-specific to find this exact bug, we're going to start by looking for if statements that have an unsigned less than or equal comparison, where the right-hand side of the comparison is a subtraction. If that's not specific enough, we can narrow it in from there, but chances are it's going to be over-specific, and we'll need to work backwards to generalize this pattern to find more bugs. So that's what this looks like, and we can even pull out the left-hand side and right-hand side of the subtraction to get a better look at things if we need to. But let's start by seeing what this gets us. So I'm going to hit save, and I'll clear out our log. We'll go ahead and run this. I don't like this output, so let's clean it up a little bit. I'll also print the hex representation of the address so we can click it in the log and go to where that is in the binary. Now that it's done, we have a couple locations where it's finding this pattern. That's very exciting. Let's see what it found. I first want to start by confirming it was able to find the location reported by the CVE, which it does. That is great. That means our script works. Now let's look at some of the others here. This first one is a little bit complicated. We would need to create a structure here and analyze these fields, make sure that their bounds are getting properly constrained. Let's ignore this one in favor of a more simple case. I can see here a number of these are dealing with structures. All the ones that have a variable plus a constant, those are going to be structure member accesses. There's a couple here that have a constant. I'm not too worried about these, but I do see one location where we have the exact pattern we were looking for in our script. But in this case, it looks like the subtraction is being properly checked before it's performed, so this is going to be a false positive. Regardless, these are the first steps to automating the detection of bugs just like this. This pattern itself was pretty easy to find, but not very revealing by virtue of existing in the binary. You saw that we were getting false positives, and that we'd need to write a fair bit more code to start eliminating those from our results. If you're curious about this sort of thing and would like to know more, please check out our upcoming trainings at binary.ninja/training. We cover everything we talked about in this video, much more in depth, and consider how to write your scripts to robustly handle false positives exactly like this. I look forward to seeing you there. Of course, if you liked this video and would like to see more like it, tell us by dropping a like. If you don't want to miss videos like these in the future, don't forget to subscribe. And finally, happy hunting, everyone.